Hello everyone, my name is Roy Jafari, and in this video we are going to talk about MLP classification, multi-layered perceptron. This is the MLP part, and classification is a data mining task that we have been performing with different algorithms so far. MLP inherently is designed for prediction. By that we mean it is designed to predict numerical values. However, you could change it in such a way that it can also be used for classification, which the difference is you want to predict a label. It could be binary or it could be non-binary. In the example that we are going to look at today, we are going to continue working on the customer subscription dataset, which was from a bank in Portugal that basically we wanted to see the likelihood of customers subscribing if we were to call them or if we were to contact them. We have already attacked or solved this problem using different algorithms. We have used KNN, we have used decision tree, we have used naive Bayesian, and we have seen so far decision tree had been the most successful one. If you haven't watched those videos that I have tackled this problem using these algorithms I just enumerated, please stop this video and watch those videos first. In this video, we are going to use MLP classifier to see if the MLP, and if we were to tune it, is going to be performing better than decision tree. All right, so let's get to it. All right, so what we have here is the continuation of the file that we've already worked on. So the KNN, naive Bayesian, and this decision tree has already been put here, and also you can see that I've already ran them. One of the parts that we're going to keep using is that feature selection that we did before KNN. And also you saw for each of these different algorithms, we had to do a different pre-processing. But the good thing is the pre-processing that we did for decision tree is going to be enough for classification. So here we are. So the only difference that, in the first step is going to matter as far as us using a sklearn module to here do classification instead of regression is to instead import MLP classifier. And it basically changes the algorithm in such a way that now it can be used for classification. So those are the details that sklearn or the developers of sklearn have already taken care of for you. So we go ahead and just create our model and MLP classifier, and I'm gonna go ahead and even remove this part, and we fit X train, Y train without any tuning, and we see how well it does. So let's just go ahead and run this and run this part and also this part. As we know, MLP is a random-based complex algorithm, and every time we run it, it might run for a different period of time, and also it may perform completely differently. So here in the beginning, in the first run, we see even a better performance than the decision tree. But let's go ahead and run it again and see if this can be repeated. All right, this time we didn't do as well as decision tree as far as the recall, but at the same time, we didn't use as many yes predictions. So we can see that the classifier is, within one of the best ones, even without having tuned it. So here we're going to, run this one more time with random state 5, and we know what random state does here is because we want to be able to, once we run this, get the same performance regardless of how many times we run this or on what computer we are going to be running this. So if you use random state 5 with this train and test set, you're going to receive the same performance every time. So here we see, as not as good as a performance of a decision tree. So our goal is going to be able to tune MLP so we can reliably get a good performance. So let's continue here. For tuning in the prediction video, if you have watched that one, if you haven't, go ahead and watch it first. We did use a tuning approach that we basically did ourselves by looping through different possibilities of the hyperparameters. However, there are easier ways as far as coding out there. I mean, you could be using the grid search CV or grid search cross-validation from the sklearn model selection module that we have. So I've already imported this one from the model selection, and you have seen me use this in previous videos. So that's why I don't have it here. But I'm also going to use another module, another function from the model selection, the sklearn.model selection, and that's shuffle split. So when we set a value for CV cross-validation, it's going to split our train set or the data that comes inside by that many portions. So if it's 5, it's gonna split it to 5. And MLP is a very complex algorithm, and such type of high demand tuning is going to last a very long time. So here we want to sort of get this function to not force us to do a cross-validation, but basically do a train test and sort of like tune MLP without having to do so much computation. If you have the time and the interest to see how much that's going to change the computation and also the performance of the tuned MLP, by all means give it a try and see if that's going to work out for you. The only thing you need to change is to change this to a number. If you want a cross-validation 5, just put this 5 and that's just gonna keep running for you. However, if we want to just use this function but don't use cross-validation, basically use a train test set the way we did ourselves, we have to use the shuffle split from the sklearn.model selection module and basically say we want to only have one split and this is my train test size, and then pass that as CV here. And now this is not going to be doing cross-validation. And we did see that MLP has so many different possible hyperparameters. I mean, all of them are actually listed here, right? So there are so many different hyperparameters that you could be at the same time at once tune them, but it's going to last a good bit of time. So here I have, made this a little bit simpler because this is going to be difficult. This is going to last a long time, so it will be just so long. It would be hours. So even fast forwarding it in the video is not going to make sense. So we could improve the performance even better if we want to invest the computational cost to tune even better. But here in this video, we just do what we can. So in 2 steps, in the first step, I only tune activation, stallware, and learning rate. And then in the second step, whatever those values come to be, I then only tune the hidden layer sizes, and the rest can be the default values. And we're just gonna tune as much as that. But if you are willing to tune more, I have the code here. You can tune even more with this code if you were willing to. So let's go ahead and click hit here, and once you do that, it might give you a possible combination of different answers based on just, randomization occurs. I mean, one of you might get, what I get here, ReLU, Adam, or inverse scaling, or someone else might get different things, right? So this is a highly randomized algorithm, and every time you might get a different tuning. And one thing I have done here that we used to do in our own loops, we would sort of like put a report out and say, okay, this combination was done. Do you remember we would print the indexes of our loops? So here, if you want to sort of like see the same thing, you pass a value to variables. The lower the value that you pass, the less amount of report this grid search cross-validation function is going to give out. If you pass higher values, 10, 15, it's going to give you like more detailed report. I have put as 2, and I think that's enough for our purposes. So let's go ahead and run this and see what this is going to do for us. All right, so we have an answer here. So we have the following settings: ReLU, inverse scaling, and Adam. And we only have to put them here. We have already, the last time I ran this, I got the same things. So here in the next code, you will run this, and you will basically want to see which of these hidden layer sizes is going to be the most successful. And I'm not going to run it here, but the last time I ran it, it gave me the value 15. Like I said, tuning MLP is a very computationally expensive process. So I'm just gonna skip these and just go to the last part that we actually tune our randomization. But before we get there, let me tell you about this line of code that they have here. When we tune MLP, we do see a lot of warnings that comes from the process. And it's because some of these tuning parameters don't like each other, or run into possible cautions. And if you want to stop them from happening, or stop the Python from showing them to you, you can run these 2 lines of codes, and that's going to do the trick for you. All right, so let's get back where we were. We are going to now basically make sure that even the randomization that we use for the our tuned algorithm or tuned MLP is also tuned in such a way that we do know that the network that has been in a random way has been initialized is a good one. So here we have to have our tune set and train set, because we want to check that initialized and trained network by the tune set, and then use that trained network for the final prediction of the test set. So we do this here, and these are the parameters that I got, and the hidden layer size is 15, seems to be performing the best after I ran it. So I put 15 here, ReLU, inverse scaling, and Adam, and I am basically making sure that which randomization is going to perform the best. So I'm only using the X-tune and Y-tune for this part of the prediction. So I'm gonna hit run and see what's going to happen. All right, so here we have, if you remember from the previous videos, this is the function that we came up with ourselves, and this function pass out accuracy, recall, precision, and FSCO. One thing that I forgot to mention when we were tuning these parameters were that here I used a multi-criteria tuning. I wanted to, for the network, for the tuning, to pay attention to recall and FS score at the same time. The reason is MLP is a very flexible algorithm. If you ask it to maximize recall, it's going to do it at very large extent, such way that you perhaps are going to have higher number of yes predictions, and your maximization of recall is going to be somewhat unreasonable. Because of that, I did here, I paired it with another metric, FS score, that uses precision and recall at the same time to create that value or the metric. So it sort of like keeps it in a reasonable um, space of maximization. So that's what we did. And here, when we are running these values, we see that the FS score and the recall are not super high, and they're like within the same reasonable range. So here we see that the best one we have is when we use random state 11. So we go ahead and use this one to do our prediction, see what's going to happen. So this is it, and now here we use X test and Y test. So let's go ahead and run this. All right, we reached a much higher recall and even a better FS score. But let's see if the algorithm is using reasonably the same number of ones as MLP, as decision tree and the rest of them. So let's go ahead and run this. And it is using somewhat higher numbers of ones than decision tree and naive Bayesian, but the numbers is not that much higher for us to be concerned. If that was the case, we could certainly sort of like do what we did for naive Bayesian here as well. MLP is also one of those algorithms that you could use to extract the probabilities that the algorithm is using for driving these classification. Well, if you remember, MLP is inherently designed for numerical prediction, right? So what MLP classifier does, behind the scene, it puts 0 and 1, um, values of probability with some activation functions there to sort of like connect this, these classes to the independent attributes, right? So when it comes for MLP to actually calculate its expectation, it spit out a probability-like value. So those probability-like value can be extracted from MLP classifier as well. And just like what we did for naive Bayesian, we could also sort of like manage to have a certain number of yes predictions based on the threshold we put for at what point we want to accept a yes prediction. If you remember, we would only accept a yes prediction for naive Bayesian when the probability of it being yes was so high, 99.9999. The same thing could be applied here, but the difference with the number of yes prediction is not that much for me to be that concerned. All right, so in this video, what we did, basically we use an MLP classification, MLP classifier from sklearn module to tune it and then apply it to the same data set that we have been working on with the other algorithms and compare their performance. And we did see MLP will cost you a lot of computation and time for tuning, but it sounded that it's worth it because it reached the best possible performance.